Okay, so now let's see how we can reduce derivatives. And first of all, let me explain what is it that I mean by reducing derivatives. So remember, in the end of the chapter on the entropy, we saw as an application how to show that the internal energy for an ideal gas is only a function of temperature. And we did that by showing that, sorry, it's not like this, by showing that the partial derivative of the internal energy with respect to volume at constant temperature for the ideal gas case is going to be equal to 0. Okay, so we had to calculate this integral and express it in terms of, if you like, experimentally friendly types of derivatives. Okay, so why is this? Because, okay, internal energy is something that you cannot measure. Okay, if you have a system, for instance, a hydrostatic system or an expansive system like this, things that you can measure include the coefficients that we had introduced in the very beginning of the course. So remember, things that can be measured and are readily tabulated for these systems is the coefficient of thermal expansion, so that's change in volume with respect to temperature at constant pressure, and here is 1 over volume. There was also the isothermal compressibility, and that was minus 1 over V, and here you have change in volume with respect to pressure at constant temperature, and also the two heat capacities. Okay, the heat capacity at constant volume and at constant pressure. Remember, that would be the reversibly absorbed heat into the system whenever you raise the temperature infinitesimally by dt and reversibly, and you keep the volume constant. And in case you have heat capacity at constant pressure, what you do is you keep the pressure constant. Okay, so these are things that can be measured. Specifically, the heat capacity at constant pressure, that's much easier to measure. Keeping the pressure of a system constant is a lot easier than keeping its volume constant, for instance. So these kinds of things are things that you can actually measure. For instance, internal energy is a thing that you have no access to, or things involving entropy and things like that. Okay, so there is a general procedure to take any derivative like this that includes extensive and intensive variables. That's important. So in this case, we have the volume, which is extensive, we have the internal energy, which is also extensive, and the temperature, which is intensive. So you can take any such derivative and you can express it exclusively in terms of B, T, and P, and these coefficients, which are derivatives involving these three variables that are tabulated. So this heat capacity at constant pressure, actually, let me write it down a little bit more explicitly. Remember that the reversibly absorbed heat by the second law and the Clausius theorem in particular, it's TdS. Okay, so this is TdS divided by dt at constant pressure, which is nothing but, let me move it a little bit more that way. So this is the temperature times the partial derivative of entropy with respect to temperature at constant pressure. So this specific partial derivative of entropy is directly measurable and it's tabulated. Okay, so whenever we find any of these derivatives, we're done because we know these things. Fine, so let's see how we do this. Okay, so let's see how we express things like this in terms of the things that we have in the right hand side. Let me see if I forget to say anything. Nope. Okay, so let's see the general procedure. This is actually taken from the book by Herbert Callen. That's where this method is laid out explicitly. So, okay, first thing you have to do is to identify any function of state that you have. So U, S, or F that we just defined now, or the enthalpy, or the Gibbs potential. So any of these guys. Whenever they appear in a derivative, you have to use the properties of the partial derivatives that we saw before in order to bring these guys to the numerator of the partial derivative. Okay, so in this specific case that we have here, we already have the only function of state present, which is the internal energy, in the numerator. So we don't have to do that. But I don't know, imagine that we have this, right? So partial derivative of volume with respect to u, well, that is equal, by the properties we saw before, to the partial of u with respect to v at constant t to the minus 1. Okay, and then we work with this to the minus 1. Fine. Let's delete this anyway and write what we had before. Partial with respect to v at constant t. Okay, so that's the first step. Bring the, well, yeah, I can write it. So bring thermodynamic properties to the numerator. Then, and we do this using the properties of the partial derivatives, right? So then the second step is to, because we have things like, for instance, that or like this in the numerator of some partial derivative, because we just flipped all the partial derivatives that involve u, s, f, h, and g, we have to replace this differential by the corresponding fundamental thermodynamic relationship. So remember, for energy is TdS minus PdV. So whenever you see a du in the numerator of a partial derivative, you have to write this explicitly. But if you find, say, the s, well, let's just write the energetic ones. So the f was minus s dt minus PdV. That's what we found. Yes, we did it explicitly in the previous video. And the h is TdS plus VdP. But the g is minus SVT plus VdP. Okay, so this is what we have to use. And then after we've done that, we operate and simplify. And we may have to use again the properties of the partial derivatives. And we actually may have to repeat these steps 1 and 2 several times until we finally got rid of every single one of the properties of state. Okay, all the u's, f's, h's, and g's are gone from our expressions. And so finally we can use again the properties of the partial derivatives to bring into our final expressions the things that we do know, which are the coefficient of thermal expansion, the isothermal compressibility, and the heat capacity at constant pressure. Okay, and this is always possible to do as long as you have a derivative that involves extensive and intensive properties together. Okay, so they cannot all be extensive or all intensive. This wouldn't work in that case. Okay, fine. So let's see how we can use this procedure in general to solve our problem of the partial derivative of u with respect to b at constant t. So how we do that? First step, partial derivative of u with respect to v at constant t is already done because our energy is in the numerator. So what we do now is to replace this du by the fundamental thermodynamic relationship. So that would be TdS minus PdV divided by dV at constant t. This is not the mathematically nicest way to do it. Actually, a mathematician would probably not like this, but we are not mathematicians, we are physicists, so we don't care. So here we operate and we find partial derivative with respect to S with respect to volume at constant temperature, and this dV goes with that dV and we get minus P. Okay, good. So we came from this expression and we ended up in, okay, pressure, that's acceptable, temperature, that's acceptable, but this is still complicated. Okay, so this is still something we don't know what it is. So wait a second, where did I see the entropy last? Was it one of the things that I do know? I know the heat capacity at constant pressure, so I know the partial derivative of entropy with respect to temperature at constant pressure. But this is not the derivative that I have here. I have S, V, and T. Okay, so how do we solve this? Well, we have to resort to the Maxwell relations. So where did we see the partial derivative of S with respect to V at constant T before? Well, that's actually the third Maxwell relation, which says that the partial derivative of S with respect to V at constant T equals the partial derivative of P with respect to T at constant V. So you see we get rid of the entropy using the third Maxwell relation. Okay, so we do that and we just replace this that we found, partial derivative of P with respect to T at constant V. Okay, now the final step of our general procedure is to try and write this derivative in terms of alpha or beta. Okay, so is this already alpha or beta? It's P, T, and V. Well, let's see the definitions. This is not the one, and this is not the one either. Okay, so it's none of this. We would have to work some more. And how do you work some more? Well, using the properties of the partial derivatives. Okay, so what can we do with this derivative? What we know is that the partial derivative of P with respect to T at constant V times the partial derivative of T with respect to V at constant P times the partial derivative of V with respect to P at constant T. This is equal to -1, and here I'm using the property, the cyclic property of the partial derivatives. Okay, and this is the thing that we want. So this thing that we want equals minus the ratio of partial derivative of VPT, which is this one. I put it on the left hand side, and this one I put it in the numerator, so I flip it over, partial derivative with respect to T at constant P. And this guy here is indeed VTP, so that's coefficient of thermal expansion multiplied by the volume. Okay, so this is what it is, because we see the definition of the coefficient of thermal expansion is VTP, but it has this prefactor of 1 over B, and we have to multiply by that. And then in the denominator we get the other thing. We get the minus volume multiplying the isothermal compressibility, which is the partial derivative of B with respect to P at T constant. But this is multiplied by minus 1 over B. So that's why we have the minus B here. So this minus goes with this minus, and this volume goes with this volume. And what I get in the end is the ratio of alpha to BT. Okay, so this is this derivative here. And we can write it like that. So this is alpha divided by BT. Okay, so that's how we have transformed, in principle, a complicated and non-experimentally friendly derivative, which is the partial derivative of something that you cannot measure, like internal energy, with respect to volume at constant temperature. And we put it all in terms of readily measurable quantities and tabulated properties of materials. Okay, so in the synchronous session, we will do more complicated examples, and there is actually a very long and complete example, again taken from the book by Herbert Cullen, already in the lecture notes, which is worked out in detail. That's your section 8.13. So we are going to be doing this in the synchronous session. I encourage you to go and take a look and try it yourself. You have to repeat these steps several times, but it's really very systematic and mechanical. There's no magic here. You just have to be systematic and apply in order these steps 1, 2, 3, and repeat as many times as you need to. Okay, so another thing that we are going to see in the synchronous session is the TDS equations. That's section 8.18 in the lecture notes, and applications of the TDS equation. And what we're going to do next in the last couple of videos is to focus on the physical interpretation of these quantities that we have just introduced. Okay, so we introduced them from mathematical convenience to derive Maxwell's relations, but actually these things, it makes sense to think of such functions in certain specific thermodynamic situations, right? So we're going to see how these functions come into being and what do they mean. And okay, so we're also going to introduce a new set of this type of functions, which are not based on the energy but based on the entropy. These are the entropic potentials, and hopefully in the end we're going to justify why these things are called thermodynamic potentials. Okay, so all of these guys are thermodynamic potentials. The term is something we have to justify yet. Okay.